Hello everyone, today we'll talk about the problem special array with x elements greater than or equal x. We're given an array and we want to either give a number x such that there are exactly x elements in that array that are greater than or equal to x, or say that such a number doesn't exist. Now we want to find a solution to this problem that's faster than n squared, and the main observation that we're going to use is that if we have an array, we'll consider it sorted first. So let's say 5, 6, 6, 7, 7. Then when we consider different values for x, and we count how many numbers are greater than or equal to x, then for every possibility here, that's all the numbers. So in that case, the value would be 7. Then for things that are greater than 1, less than or equal to 3, the value will be 6, the value will be 5, and so on. And after the last one, the value will be 0, as no values will be greater than or equal to the value. And we can use that monotonicity, of course, as is typical, to binary search the answer, because we know that the answer will be within some reasonable bounds, like from 0 to the number of elements in our array, and we can just find the value for which the number of elements that are greater than or equal to that value is equal to it. That check can be done with simple linear path through the array, and then that will already give us a solution that's n log n. We might also consider, if we already sort the array, that we can find the point at which this value would be in the array and count how many elements are to the right of it. So that is another way to use binary search to solve this problem. But another way to do it is just to notice that we can simply go through all the elements, through all the blocks of same elements, and consider if it's possible to find a solution in between those blocks. So here you would have 0 elements that are greater than that value, so that it would be impossible. And now if we look here, we have 2 elements here. This value is equal to 6. So we have one option. Is 7 okay? And 7 is not okay because there are 2 elements greater than it and we would like to have 7 elements. Okay, so we take another block. Now we have 4. And we ask, and here the next number is 5, and we ask if in this case 6 would be a correct solution, and it wouldn't because there are 4 elements greater than it. We take another block, and now we can consider any answer between 4 and 5. And you see that here we have 5 numbers that are greater than it. And indeed, we find the answer is equal to 5. And indeed, for the value 5, there are 5 elements that are greater than or equal to it in our array. And we can implement it just in a straightforward manner. So we sort the numbers. I add a sentinel value 0 for ease of implementation. You can skip it, and then you'll have to modify the rest of the algorithm. And we just remember the last value we've seen, because we want to consider whole blocks. We cannot split in the middle of a block. And how many values we have already seen to the right. We go through all the numbers in non-increasing order, so from the largest downwards. And if the block has ended, so we found a value that's different than the previous value, then for anything between the current value, not inclusive, and the last value we've seen inclusive, we can consider it as a solution. So in this spot, we would have only a 7, in this spot only a 6, in this spot between 3 and 5, you would consider either a 4 or a 5. And any of those can be a solution, and which one is a solution? Well, we know how many elements are greater than or equal to it, because that's just the count. So if the count lies exactly within those bounds, then it is indeed a solution and we can return it. And of course we always have to remember the last element we've seen, and also the number of elements we've seen. And if we haven't found a solution here, we'll just return -1, as this is what we have to return if that number x doesn't exist. And one way to make it faster than n log n is to notice that we can sort this array using a counting sort. Since if the numbers aren't too big, of course, counting sort is fast, but even if numbers were big, there is no reason to consider numbers bigger than the number of elements in the array. We might as well just change them into n, where n is the number of elements in the array, and then we have bounded elements and we can use a counting sort to have a linear time complexity.